So the way we express this is using
The Kronecker
Kronecker
delta. Jinx!
Folks, this is Bari, Brown University graduate student in physics.
And my name is Suborno Bari, and I'm doing my BS in Math and Physics at NYU.
And today we're checking out the next part of general relativity, which is tensor algebra. Today we're going to do three main operations with tensors: addition, multiplication, and contraction.
Contraction?
Yes. So let's check them out. Are you ready? So let me begin by where we ended off last time. First, let me write down the rules of transformation for our two types of tensors. Do you want to write them out, or do you want me to?
Sure, I'll write them out.
Okay, so you write them here.
Let me put my phone. So.
Okay, you do contravariant. I'll write the tensor transformation for covariant.
Wait.
So you write the transformation for this one.
Oh, gotcha. All right, so it's a little bit cluttered over here, but contravariant is essentially if we have dy in some random direction. What index could we use?
While you do that, I'm gonna write down the
Wait,
other rules.
what index should I use?
It's just whatever you want, M.
Okay. dym is just the sum from. It's just the sum over some dummy variable, let's say p, of partial ym partial xp dxp. Or in other words, kind of the chain rule.
Yeah. Okay. Let me write down the. Do you want to write down the covariant tensor?
Sure. I'm fine with that. So we have ds dym is equal to the sum over some dummy variable p of partial s partial xp partial ym.
Okay, so great. So now first,
Sure.
Okay, so those are the tensor transformation rules we've been talking about in the last few lectures. These are the rules that we derived in the last lecture. So today I want to show you why tensors are so powerful, starting from these two transformations that we have here. The first important thing about tensors is this. If a tensor is 0 in one frame, in one coordinate frame P, then it'll be 0 in all other coordinate frames. Okay, so that is something that makes tensors special.
Why? Is it because if we plug it in over here, it gives us 0 on the other side, no matter what?
So for example, if a vector is 0, that means all of its components are 0.
And it doesn't matter what linear transformation we use, it's always the 0 vector.
That's right. So let's say you have this small step, dxm. If this small step happens to be the 0 vector,
but then it's not a small step.
Then it's not a step at all. But then for all m, this vector is just the 0 vector, right? So now if I plug that in here, then in any other coordinate frame, what is dym?
What?
If I plug in
0,
dxm is 0,
then this is always going to be 0 no matter what. All of the summation is just going to be 0.
It doesn't matter if you have a contravariant or covariant.
Yeah. If you plug
dx,
no, that's not the one.
Here.
That's not the one to circle. If this one is 0, then it doesn't even matter. This is always going to be 0.
Okay, so that's right. So you see, if a tensor is 0 in one frame, it's 0 in all frames, right? But even more importantly, if a tensor equation is true in one frame, it's true in all frames. So let me show you what I mean. Let's say that I have a tensor t, okay? And let's say I have a tensor s, okay? Let's say that in some coordinate frame, they're equal. Okay, so for example, this is a tensor t with some indices, okay? Here is a tensor s with some indices. Let's say that these two tensors are equal in one frame. Then guess what? They will be equal in all frames.
Okay.
Can you show why this is true from this?
Well, how would this? Well, this is just an extension of this, isn't it? So, let's see. Why could this be true? Maybe it has something to do with this.
That's right.
So.
Do you want to see?
Wait, can I try? That's extremely interesting. So, I mean, if this is always 0, then they're always going to be the same.
So they're always going to be
Holy
the same.
crap.
Yeah. So if two tensors are equal in one frame, they're equal in all frames. So that means if you write down a tensor equation in a specific coordinate frame, it will hold in any reference frame. So everyone can agree on that equation. Okay, so now we're going to talk about the three main tensor operations. First is addition, multiplication, and then contraction. Okay?
Is that a spring?
Yeah, that's right. So we're going to, these are the three main operations you can do with tensors.
Is this just like the cross product, or is it something beyond that?
That's a good question. We'll see right now. So first, let's start with addition. So give me the red marker.
I'd imagine addition would be pretty simple, right? Just add every single one of the components index by index.
That's right. Exactly. Yeah. So let's say you have, let me start with.
Wait, can I take my marker back?
Yeah, 1 second.
Wait.
What?
Okay. So can't we just say if we have, and they have to have the same index, they have to have the same number of indices, of course. So if we have A, M, N, P, Q, R, and then B, M prime, N prime, Q prime, P, oops. And then we have B, M, N, P, Q, R, then C, which is equal to A plus B, C, M, N, P, Q, R, just equal to A, blah, 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 plus B, blah, blah, blah. And of course, there's some hidden summation notation, but.
Exactly right. Exactly right. So if you want to add two tensors, that means they have to be the same rank. So rank is just the number of indices that the tensor has. For example, this is a rank 1 tensor, this is a rank 2 tensor, this is a rank 3 tensor, so on. And
they have to have the same dimensions.
Right, so they have to have the same number of contravariant
and
covariant indices. Okay, so for example, even though these two tensors have the same rank, they don't have the same number of contra and covariant indices. But these two tensors do. So only now can you add them.
Interesting.
So, exactly. So this is tensor addition. Very simple, right?
But what about multiplication?
Yeah, multiplication is also very simple.
Is it like vector multiplication, matrix multiplication, and then so on?
It's actually like regular scalar multiplication.
Really?
Yeah. So let's say you have two tensors, T, M, and let's say X, N. When you multiply them, that gives you a new tensor with one contravariant and one covariant index. That's it. Very simple, right?
Can we get an example?
So let's say, yes. So let's say you have 4 vectors. So I'll explain what that is.
Are they just vectors with 4 components?
Yes. Exactly like we have in real life, right? 1 time and 3 space components. So let's say you have 2 tensors like this. So both of these are rank 1 tensors. That means they only have 1 index, and they both have contravariant indices. And they're 4 vectors because they just have 4 components. Now, if I multiply them, let's say that gives me a new tensor, SMN. Sometimes people show tensor multiplication by this, but we don't need that. Okay, keeping it simple. Okay, and each component is just the product of the individual components. So first you might say, how many components are there? You want to take a guess?
Let me think. 8?
There's actually 16. So 1 for each combination of product you can have.
Oh.
That's right. So the first term would be U1, V1.
But that means that multiplying 2 vectors gives us a matrix?
That's right. U1, V2, U1, V3.
So this is not the dot product or the cross product.
Yeah, it's kind of like how you multiply vectors, yeah. So U2, V1, U3, V1, so on. So that's how you multiply 2 tensors. And that gives you 16 components in this case. 16 components if you multiply 4 vectors. Okay, good?
Interesting.
And here you don't have the same limitation as with addition, In tensor multiplication, you can multiply tensors with different
rank
and different number of indices. Different rank and different number of contra and covariant indices. Okay, good. And the final.
But what's contraction?
That's right. So we're gonna see that right now. So contraction is.
That's there. No way. That's the symbol.
Yeah. So I'll show you what contraction is. So first, to understand contraction, let's say we have a function f. Okay. Let's say I have a function f. And let's say this function is a function of several variables y1, y2, all the way to yn.
Is it a scalar or vector output?
And let's say it just gives you some kind of a scalar output.
Got it.
So now I ask you the question, what is...
That is definitely a
change in the function f with respect to a variable x.
That's just a partial derivative.
Exactly. First you might ask, where does x come from? Well, each one of these y variables depends on x. So y...
Oh, so we've got a kind of parametric function situation going on here.
Exactly. Each one of these y variables is a function of x, and f is a function of these y variables.
So we've got some chain rule action.
That's right. Can you write it down? Do you want to guess?
So it's just partial f, partial yk, partial yk, partial xa, which is exactly the same thing that we saw all the way back here.
Very good. So now, let's say that this f is a coordinate xb. Okay? So I'm just going to replace what you wrote here with xb. xb. Partial y. Partial yk. Partial xa. Now, first of all, you agree that repeated indices means a summation over k.
Yes, that's Einstein notation.
And now, this just simplifies to partial xb, partial xa. Now, if x, b, and xa are independent coordinates, you want to guess what this would be? Let's say that b is equal to a.
Wait.
What would this be?
But then the whole point is moot. This is just 1.
Okay. So if b is equal to a, then this is equal to 1. What if b is not equal to a? Let's say you have orthogonal coordinates here.
Is it 0?
It's 0. So the way we express this is using
the Kronecker delta. Jinx.
Yeah, variant index here. And a is my covariant index here. So this derivative here is just equal to the Kronecker delta. Okay,
interesting.
Good? So this is the setup. So keep this in mind. Now let's explore what contraction is. So going back here. So let's say we have the following. A tensor T, which is equal to the product of two vectors. Let's say u and v. And let's say that one of these vectors has a contravariant and one of these has a covariant component. Okay? How does this tensor transform? In other words, what is T, M, N prime?
Hey, wait a second. Didn't we explore this last time?
Yes. So go ahead.
So
then write down what our transformation law is.
I believe it should be u... Wait. Is it? I think so. It should be u m prime v n prime times partial. I'm having trouble remembering, but I think it's. Let me take a look at it's contra. Wait, but last time we did it for I think two contravariant ones. This time we're doing it for both contra and co.
Yeah. Do you want me to show you how to do it?
Can I try?
Okay, go ahead.
Okay. So we know the transformation rules for contra. So we know dym is going to be equal to we sum over p. This is just partial ym partial xp dxp. And then we know the same thing for cove. We just have this. Okay, so now let's actually do this thing. So actually doing the transformation, all we have to do is first take this. So this is just going to be what? The sum partial ym partial xp dxp. But wait, we're actually using u and u prime, so we gotta account for that first.
You can keep that y.
Okay.
You can make the dx.
Oh, oops, sorry. I'm blanking here. So this is UP, and then we should be able to write VP partial XP partial YM.
So use a different dummy variable here because
yes.
Different.
So do we have this?
Perfect.
Or in other words, this? Partial x cubed partial yn.
Okay, perfect.
Oops.
Okay, good. So now let's take a look at what we have here. Okay, so right here we have the original tensors UP, VQ. Okay, and then let's see what you have. Partial ym, partial xp. Okay, that looks good. And partial xq, partial yn. Okay, so now take a look at what we can do. See, this looks very familiar from what we did with the Kronecker delta, right? So that means I can just replace all of this with what?
Oh, wait a second. This is all, but wait.
Oh, no, this is separate. So make sure you keep that. Don't forget about that.
Oops. But wait, these are two different dummy variables, while these two are the same. Does that have any implications?
Since they're dummy variables and you sum over them anyway, they're just going to be left with, they're going to die out at the end. So you don't have to worry about that.
All right.
Here I just made you use different dummy variables just for
clarity.
But at the end, they're going to get summed over. So they're not going to be there.
All right, I'll take your word for it. So don't we then just have partial, Q and P?
Okay, perfect. So now let's write down what you found. You found that UMVN, so this is our original tensor. T is UMVN, and then our transform tensor is equal to UMVN prime, and you found that's equal to delta QP UPVQ. Now, what is this? Delta QP. What is delta QP? It's always either
0 or 1.
It's always either 0 or 1. When is it 0?
It's 0 when they're not equal.
When P is not equal to Q.
Oh, now I see why it doesn't even matter, because if they're not equal, it gets zeroed off anyway.
Yeah.
So they're practically equal.
Exactly. And if they're equal?
Then P is 1. So that means we're essentially just summing UK VK.
Exactly. So this reduces just to, well, use one of them here.
Okay. UP VP.
Okay, good. So this
UP
reduces to this UP VP, and that, remember what's on the left hand side, UM. When we did contraction, what we did is we set one of the upper indices to one of the lower indices.
So we're combining them.
That's the key idea. I said,
wait.
So no, that's what contraction is. Let me just show you. What we did, we set this index equal to this index. That's what contraction is. That's the big idea of contraction.
This is insane.
You set an upper index equal to a lower index. That's why this becomes like this. Okay? That's why this n becomes an m. And that lets us reduce it to a delta. And so this actually is an m. It's not a typo. Okay? UMVM prime is equal to UPVP.
Wait.
But UPVP are just dummy variables. So that means if you contracted the tensor, then UM_VM prime is just equal to UM_VM.
Wait, so I have a question.
Okay.
Does that mean that when we're doing contraction, are we just multiplying by the Kronecker delta?
Contraction is very similar to the dot product. Very similar to the dot product. You want to see why? Because if you have a vector t, mn, is equal to UM_VN, right? If I contract the vector, what I'm doing is, give me the red, is I'm setting one of the upper equal to one of the lower index.
So this is just effectively multiplying by the Kronecker, right?
Well, you'll see. Then I just have UM_VM. But what is UM_VM? That's U1 V1 plus U2 V2. Oh, this looks like a V.
Yeah, so it is multiplying by the Kronecker delta.
And this is just the dot product of the two vectors.
Wait, is this permanent? No.
Look, this is just the dot product.
But wait, just think about it a little bit more. Also, because the dot product doesn't work on higher rank tensors.
That's why contraction is a generalization of the dot product. That's what contraction
Yeah,
is.
so here's the thing. We're essentially just multiplying by the Kronecker for every single component of our new sum. So originally, if we have 4 vectors, we might have U1, V1.
Can you use the black?
Yeah, okay. We might originally have U1, V1 plus U1, V2 plus U1, V3 plus U1, V4, then plus U2, V1 plus U2, V2 plus U3, V3 plus U4,
But here's why that doesn't come in here. Because when we contract, we set the two indices equal. So they're both the same.
Yeah, that's what I'm trying to show. Yeah. Okay. Oh, yeah. So, U2, V4. Then, I mean, it just continues on and on. But the thing is, all we have to do is multiply every single term by the Kronecker delta at that point, A, B. That means this one is conserved because you multiply by 1. This one goes away because you multiply by 0. This one goes away. This one goes away.
Good.
This one goes away. This one is conserved. And so on and so forth.
Yep, that's the same way of showing what we showed here.
So that's the delta, the dot product are the same.
Yeah, this is the general relativity version of the dot product, the contraction. And let's see. So, did I miss anything?
I don't believe so.
That's
You've done
Thank
addition,
Let me just
multiplication, and contraction.
Yeah, I need to say one more thing.
yeah, absolutely. The lecture was very nice.
Thank you. So,
I hate you.
so now you might wonder, why is it called contraction? Okay.
I have a question. I have an idea. Maybe because we're going from a high amount of indices to a lower amount of indices,
That's
so we're
exactly
contracting
right.
it.
That's exactly right. So let's say you have a tensor T with a few indices, let's say M and P, every letter you can think of in the alphabet. If I contract this tensor, then I set one of the upper indices equal to one of the lower indices. So choose any of the upper index.
M.
Choose any one of the lower index.
R.
Okay. So now if we set them equal, it doesn't matter. You can set M to R or R to M. Why doesn't it matter?
Because, I mean, they're just dummy indices at the end of the day. We can swap around the names.
Exactly. So which one do you want to set to which?
I like M better than R, so
Okay,
replace
so
it.
let's set the variable R to M. So then we have tensor M and P, Q, M, S. Now, what is the rank of this tensor?
It's normally 6.
It's a rank 6 tensor. What's the rank of this tensor?
5.
No.
Wait a second. It's still 6?
4.
What?
You just killed 2 of the indices. Because you see this M, even though I wrote it down, it doesn't exist. Because I'm summing over.